Good morning, and welcome to the conference. I know it's 8:45. It's not exactly the time for those of you from San Francisco to wake up and started attending work. It's almost an hour earlier than usual. So thank you very much. We'll make it worth your while. All right. So to get started, I want to talk about how we got here. And to do that, let me tell you the story of Lester. 10 years ago, 2008, Lester was a PhD student at the UC Berkeley Amp Lab studying machine learning. And 2008 was a very special year for Lester. Around then, Netflix started the Netflix Prize, or the Netflix Challenge. All right. Now you preview 4 more other slides. Maybe you've learned about how Spark started. How many of you remember the Netflix Prize a decade ago? Quite a few of you put up your hands. For those of you that don't remember or don't know about it, the Netflix Challenge, Netflix as a company anonymized 100 million movie rating datasets from their users and started a public competition. In that competition, anybody could participate. Whoever could come up with the best recommendation movie algorithm will win $1 million. It is $1 million, and that's a lot of money for Lester, who was a poor PhD student. But more importantly, Lester has been working on toy academic machine learning problems without access to real-world data sets. When he saw this competition, he jumped on it. Now, to actually win the $1 million and to come up with the best recommendation algorithm, Lester wanted access to a lot of data. He wanted access to all the data, as a matter of fact, in the data set. Why? Now, to illustrate with a very simple example, let's imagine Lester wanted to build a predictor for a specific movie. The only feature he has is the age of the user. In this case, you have seen on the screen, there's actually 4 data points. Maybe there's actually a correlation between age and the rating the user would actually give on this specific movie, but maybe not. What happens if you want to predict the rating this particular user would give to the data set? It's kind of unclear. Now, imagine you have a lot more data. It becomes very obvious for a user of this particular age, it's very unlikely the user will rate the movie highly. So Lester, in order to win the data set, Lester wanted access to all of the data to be building his machine learning models. And to do that, he had to scale out beyond a single machine because he couldn't fit all the data sets on his laptop. And he looked around. He found Hadoop was actually the leading framework for doing distributed data processing back then. Let me start prototyping my machine learning algorithms on Hadoop. But very soon, Lester realized this was incredibly slow and painful, because for every iteration of the machine learning algorithm, Hadoop needed to go back to disk to be scanning the data. Now, the Amp Lab in 2008 was a very special place, especially in academia in the sense they put together a diverse group of people. There are PhD students working on systems research, distributed systems, and there are PhD students working on machine learning, and they were sitting under one roof. So Lester walked down the aisle. Matei was right there, and who we all know today as the original creator of Spark. He talked to Matei and said, Matei, I think if you were to just give me a couple primitives in the system, I could actually leverage that to solve the problem I have at hand, which is to build large-scale recommendation algorithms on large amount of data. So a weekend later, 600 lines of code, first version of Spark was born. It was later renamed Apache Spark after donating the project to Apache Software Foundation. And Spark became the first unified engine that combines the best of big data processing as well as building machine learning models directly on top. Now, you might be curious, like, what the hell is going on with the Netflix Prize? So Lester was part of the ensemble team. And they actually created the best recommendation algorithm tied with another team. But they submitted the entry 20 minutes late, and they lost $1 million. Here's a picture of the other team happily accepting a $1 million check. If Spark were invented 20 minutes earlier, Lester might have been $1 million richer. That's how important it is to be efficient. But life wasn't so bad for Lester after all. He became a faculty member at Stanford University. And really, the story of Lester doesn't just end there. Look at where we are today. Spark has 500,000 meetup members around the globe. It is used by a lot of people every day. According to Stack Overflow's 2016 developer survey, Spark was rated a top-paying tech, which indicated tremendous demand from employers. Time to ask for a raise. And in 2017, actually, what struck me the most was Spark was rated one of the most loved technology by developers. It is used everywhere, from leading internet technology companies like Facebook all the way to powering state-of-the-art physics experiments at CERN. And more importantly, look around you. There's 4,000 of you here today to celebrate Spark and Spark+AI. This is the first year we renamed the conference to explicitly include AI and how Spark can work together with a lot of other AI technologies. And on that note, I want to introduce you to a new project we've been working on called Project Hydrogen. And the goal of Project Hydrogen is to enable first-class support for all distributed machine learning frameworks on Spark. Why does people love Spark? I think the real reason, while a lot of you were drawn to Spark initially because of the 100x speedup over Hadoop MapReduce, but the real reason people love Spark and stay with it was because of the unified nature. For the first time in history, you could actually write a single data pipeline in a single program that reads a lot of data for a variety of data sources, be it object stores, distributed file systems, relational databases, or even streaming message buses. And it could prepare, transform, clean your data, and then directly be running machine learning models on top of them, all in a single unified data pipeline, which means it's much easier to debug, test, and operate. It was incredibly difficult to even write a single test case that could cover your entire data pipeline before Spark existed. And now it's actually possible. But in the last few years, there's another megatrend that happened. In this megatrend, it was the explosion of machine learning frameworks. Starting with MLlib, TensorFlow become an extremely popular option, MXNet, PyTorch, CNTK, and a lot of other frameworks, and new ones are popping up every day. We're increasingly seeing Spark users wanting to combine Spark together with these frameworks. But when you use just MLlib, you have a unified data pipeline. But when you try to use other frameworks, the unified nature starts to break down. And we see users primarily using two different options. The first option, this clicker is really flaky. The first option, there's one cluster running Spark for doing the data prep. And there's another cluster running some distributed machine learning framework. It's not Spark on the side. And Spark is used for data prep and will load and write the intermediate data onto some shared storage, for example, a distributed file system. And then the machine learning framework should be reading from a shared storage. The big problem is you created two disparate systems, and it actually breaks down the unified nature, which means now, even just to develop, you have to understand exactly how two systems work. They might have very different debugging schemes, different logs files to get to. It's very difficult to test. Just writing a single test case in Scala or in Python becomes very difficult. And it's also very difficult to operate. Instead, we see more and more users gravitating towards the second option, which is to create one cluster and have Spark running in that cluster, and Spark actually launches the second part of the job, which does the machine learning frameworks. Unfortunately, this doesn't quite work today. And some of you might actually already be doing it. But let me show you why it doesn't work. And in order to do that, I have to take a look under the hood at the Spark scheduler. So the way Spark works is that for Spark, each job is divided into a number of tasks. And the tasks are assumed to be completely independent of each other. And this is what we call imbalancing in parallel. And this is a massively scalable way of doing data processing that can scale up to petabytes of data. The way a lot of the distributed machine learning frameworks work in their training process, sometimes they use MPI, sometimes they have their own custom RPCs for doing communication. But one of the things they have in common is they assume complete coordination and dependency among the tasks. And what that means is this pattern is actually optimized for constant communication rather than for large-scale data processing to scale up to petabytes of data. What happens if one of the tasks fail? In the Spark's model, if a task fails, because the tasks are independent of each other, we just need to launch that task and that task alone. And that's enough for fault recovery. But in the case of the distributed machine learning frameworks, if one of the tasks failed, because there's complete dependency, all the tasks needs to be launched. And if only a subset of a task, only even one of the tasks gets launched, that task will actually wait there for all the other tasks to be launched and actually hang. So there's actually a fundamental incompatibility between the way Spark scheduling works and all of these distributed machine learning frameworks work. So Project Hydrogen is a new SPIP, so Spark Project Improvement Proposal, that aims at actually introducing one of the largest changes to Spark scheduling since the inception of the project, since the original 600 lines of code. And introduced a new system primitive, a scheduling primitive, called gang scheduling. And in this gang scheduling mode, as evident from the name, the tasks are scheduled all or nothing, which means either all of the tasks get scheduled in one shot, or none of the tasks get scheduled at all. And this actually reconciles the fundamental incompatibility between how Spark runs and how the distributed machine learning frameworks need. To illustrate that, I have sort of drawn on the screen a 3-stage data pipeline, where the first stage just use embarrassingly parallel mode to do some data prep, loading data from shared storage, and then transform them, prep them for machine learning training. And between stage 1 and stage 2, there's a barrier that divides them. And stage 2, the barrier indicates to Spark, stage 2 needs to be gang scheduler because I'm running some distributed machine learning frameworks. And after training, there's actually another stage. It becomes, again, the embarrassingly parallel stage that might, for example, just apply the model directly coming out of the distributed training and apply them to test data sets, and eventually write them out to storage. The APIs are actually by no means final, but following the theme of making things easy to use, there's actually only one very simple API addition. And I want to give you the sketch, which is just a barrier function. In the barrier function, it just indicates to Spark, let's now divide the stage into 2. Everything before the barrier is embarrassingly parallel, and everything after the barrier, the next stage, should be gang scheduled. And all of the complexity actually lies under the hood in the DAG scheduler, transparent to the end user. And within leveraging all the similar functionalities in Spark, like map partitions, we usually define functions, you can now be launching the actual machine learning programs within Spark. And it will be entirely fault tolerant. Now let me show you a demo of what it looks like. So what I have here is the Databricks notebook. And I've pre-attached this notebook to a 4-node cluster that have GPUs on them. It's actually a fairly weak cluster, but they do have GPUs. And I have a custom build of Spark. This includes a prototype for the Project Oxygen work. And if you are interested in the actual code, there's actually a pull request open on GitHub. You go take a look at the changes. And I preloaded the dataset with the MNIST. I preloaded the cluster with the MNIST dataset. The MNIST dataset is essentially a collection of handwritten digits. And the goal is to train a model for digit recognition. The dataset sits in actually a Databricks Delta table that Michael will tell you more about later. I've loaded now the table into a data frame. And you can see the schema is fairly simple. There's a label, which indicates what the actual digit is. And there's a bunch of features for that indicates the elements in the image. It's actually just pixel colors. And to take a look at what the data frame actually looks like in its content. You'll soon find out why it took a while to display this. So you can see for a label 6, this is actually the data for that image. Right? It's a bunch of zeros because most spaces are actually white. But at some point, there's actually value. If you keep scrolling, you can see here. Now, I have this very simple program. Let me launch it, and I'll explain what it does. This 6 lines of code loads the data frame, repartition it to 2 machines, because I only want to use actually 2 of the machines for training here. And it calls 2pandas RDD, which is a function I just defined that converts the data in the data frame using Apache Arrow into a format that a distributed training framework actually expects. And the distributed training framework I'm running here is Hover, which is a framework built by Uber that runs on top of TensorFlow and combines TensorFlow and MPI to do distributed deep learning training. As you can see, there's a barrier interface here. It's what we've shown you earlier in the API slide. It indicates to Spark the next stage, which just runs hover, needs to be gang scheduled. And then we'll collect back actually the model and building the model. So here, 6 lines of code to build the model. This is now as simple as running some machine learning algorithm defined already in Spark and MLlib. But now, with exactly the same ease of use, exactly the same lines of code, you can actually run any other frameworks. And you get the same properties you get if you run the entire thing within native Spark code. The same set of fault tolerance properties, the same set of speedups and recovers. Now, deep learning models takes a while to train, and so the demo itself is not about deep learning. So let me actually show you applying this model that I've trained actually last night into a streaming workload. So here I have another notebook. In this notebook, we're actually reading a stream in. I pre-created 8 million actually images, send them into Kafka. So we created a streaming. I want to do live prediction on the fly. And all I'm doing here, I've created a data frame user-defined function that calls predict using GPU. All this user-defined function does, it takes the model built by an offline training pipeline that I've just shown you earlier, and I'm applying that directly to the streaming data coming in. And I'm displaying, so Xiangwei sitting there have actually pre-launched this for me, so I don't have to wait for it to be launched. But here you can see it's actually already processing 2,000 images per second directly in this 2 lines of code. And you can see the actual prediction result. Most of the time, the model is correct. 7, it was predicted 7. 3 predicted 3. Sometimes it's wrong. 2 predicted 8, and 1 predicted 6. And now I could actually go back and tweak the parameters. But it gives me a very quick way of iterating, because now I have access to a cluster and I have access to all the power of Spark. All right, so the goal of Project Hydrogen is really to embrace all the distributed machine learning frameworks as first-class citizens on Spark. We want to make every other framework as easy to run as just MLlib directly on Spark. We want you to get the unified nature of the pipeline, so you can actually have a single pipeline written in a single program that you can develop, debug, test, and operate. And the gang scheduling is actually just one of the first work we're starting. There's going to be a lot more work that we'll do to actually embrace other machine learning frameworks, first-class citizens, including speeding up actually data exchanges, because data exchanges can often become a bottleneck in all of this training. And also, we want to make Spark aware of accelerators, so you could actually comfortably use FPGAs or GPUs in your latest clusters. And hopefully, soon, you actually have a single unified pipeline that can run all the machine learning frameworks. If you're interested in joining the discussion to help shape the project along, you should go follow this Jira ticket, Spark24374. And we can actually get a lot of help from the community in understanding your use cases. With that, thank you very much, and enjoy the rest of the conference.